So this time we want to discuss about global extreme point. Global extreme point. So if you remember last time, to identify that the critical point was local maximum, we went through the Taylor's formula. Okay, remember, we compared the values of f close at fx star. We found, so okay, minus fx star was f prime at x star plus half of f second at point C x minus x star square. And for critical point, so we had this quantity 0, so the sign depended on the sign of f second close to x star and the continuity of the f second. So what if I had f second of c of t positive always? Okay, if I had the derivative positive, okay, everywhere. If I knew from the beginning that it was positive for any t in the domain of f. Okay, then if we had this, then we would have fx greater than fx star, okay, for any x in the domain. Okay, and then x star, thus x star is a global mean. Okay, so you would be able to conclude about the globality of the critical point. Now, which is good. So now remember, now what there was a function, there was a property related to this condition. If you remember, in calculus, we said that a characterization for f c2 is c2. Okay, let's say an open interval, and f second, yes, f second positive. Okay, for any t in I. So there was an equivalence with a certain definition, characterization of f, which is the convexity. F is convex. And what we gave a definition of convexity was that we had the value taken by f along the interval. So tx, let's say it's tx1 plus 1 minus tx2, okay, less than f t times fx1 plus 1 minus t fx2. So this is for any t between 0 and 1. Okay, so this is the definition of convexity. Let's move these rectangles here. Okay, so this is what we gave, if you remember, that was a characterization. Okay, so what was exactly the meaning, interpretation of convexity? It was also geometrically, geometrically it was we had, so if we were on some interval, the value taken at x1, so x2, okay, so tx1 1 minus, when t belongs to 0 1, describes the interval, this interval. So all points, any points here is we can write it as some t times x1 plus 1 minus t x2. Okay, and f taken at this point, so let's say at this point, yes, the image, it says it remains less than t times fx1 plus 1. So if this is fx1, if this is fx2, again here a linear combination like this one of fx1 fx2 remains here. Okay, so let's use another color. Okay, so let's say something here. So this one is a t fx1 plus 1 minus t fx2. So the definition says the value taken by f at these points, okay, it remains less than this level. Okay, so since it's less than this level, it must be somewhere here. So let's say we have something here. The level of this is here, but the value of this function, the image of this function, is at these levels, which is smaller than this one. Okay, and this is true for any t. For all the t's, it must be lower. Okay, now if we consider, so this is a line segment joining the 2 points. This is x1, so this is x2 fx2, okay, and this one is x1 fx1. So this line segment can be described by the points, these points and these images. Okay, it describes the line segment. That means any f at these intermediate points remains, the level corresponding must be lower each time for each t, and the point this kind will be lower. So necessarily my curve must be something like that. I have always something smaller. Okay. Okay, so this is my curve like that. So convex function, usually we keep in mind that it's more smiling. Okay, it's smiling shape. Okay, and this so to have, let's summarize now what we said. To have a global extreme point, if we have a convexity for our function, this property of convexity, it is then that here for C2 function it is characterized by 5 second derivatives, then we will have a global minimum. Okay, with convexity we can ensure global minimum point. And similarly, this idea is extended to function of several variables. So we give the definition of convex function as this one. Okay, the only thing that is different, the values are not real, taken at vectors. So we will have a point capital X1, another point capital X2, and we need to ensure that inequality like this one, to say that we have a convex function. Now the question, how can we characterize convexity? Without the definition, always characterize it using information on its derivative. And yes, we have something similar. And so definition like that also, yes, let's illustrate something, a graph, a paraboloid, so in 3 dimension, so would be like that, x, y, z. An example of convex function, we have a paraboloid. Okay, so paraboloid has a shape like a parabola. That is a parabola, yes. For example, here, if you say this is a parabola, yes, it's a convex function. Okay, any point you take, any point you join them, the value taken, okay, is remain less than the value of f taken at that intermediate point is less than the value, the segment, corresponding segment. And similarly for each time you have the values taken by f are less than the long segment joining 2 points E and B, for example, on the curve, on the surface, and you look at the values taken by f, okay, long, yes, they remain smaller. the same idea. So definition with that similar. Just think about taking A and B, okay, instead of x1, x2, or capital X1 or and capital X2, because your x1 and x2 are here. So in the plane, they have coordinates x1 and y1. And more generally in Rn also we can do that. There is something to pay attention. We are adding here to add t to say te plus 1 minus tb. So belongs to S for any t eb 0, 1. This is, if you remember, we need a certain property for our set 0, 1. This is okay for any A and B. You take them in S, and you check that for any t between 0 and the line segment remains in S. This is requires as convex as a set. Your set must be convex. So speaking of property of convexity for a function, we need to work first on the set that is convex, so that we will be able to make this, to form this line segment and compare the value of f taken on these line segments. An interval is always convex. So that's why in for function, real function, but still we specify interval, but without speaking of convexity of set. But for several variables, you need to pay attention to these properties. So it is important that you pay attention to that. Okay, you need to pay attention to the property of this property, convexity of your set. Okay. Now, we said how can I, our question now, knowing that we have convexity function, how can I characterize a function of several variable to say that is it convex or not? Because of course it is hard, it is not easy to check the definition like that. Apply that to any point of your function. Your formula can be as complex as you cannot imagine. So checking such inequality is not easy. It's not. Okay. So here are three main theorems. So let's read the theorem, explore them, understand their assumptions, and see what we can do. Okay. How we can apply them. So the first theorem says the following. Here it is. Let's move it here. So here are the assumptions. We need convexity of the set. Yes, we said about explained why. And here it assumes only C1 regularity, which is less than the one we spoke about. So there is a characterization for C1 functions to be convex. It is equivalent to check these inequality. So the difference of x and a of a, two different points, it's greater than the gradient times x minus a. Okay, so for any x and a in the domain. Okay, so also not very practical to check such inequality. You see, yes, convexity I didn't mention, but there is, depending on this on this depending on what the sign, the inequality, if you take an inequality large or strict, you get convex or strictly convex. Okay, the concave is the inequality in the other side. Okay, so the concave function have the other okay, so this is convex, let's say convex shape. This is convex shape. A concave shape is like that, is more like that. This is concave shape. Okay, so you see, this is the first theorem. It's good to know that convexity doesn't involve just regular functions, that they can be less regular. So let's explore when we have second derivatives, so more regularity. What happens? So again, we need a convex domain. Here open and open. then yes, what happens, the positivity, if you remember, for function of several variable, let's remind ourselves about this difference, fx minus fx star, you remember, it was x minus gradient of f at x star, x minus x star, plus half of x minus x star transpose the Hessian matrix at some vector and x minus x star. Remember, this is what we did. Okay, so when you have a critical point, you have 0 here. Okay, but now we need the positivity of, so we needed the positivity of the Hessian. Okay, we prove there is connection, the definition of convexity. We can write, so we compare the values of this particular quantities. Okay, so we use Taylor's formula and we prove that it is related to the positivity of the Hessian. Okay, and now the positivity of Hessian, the strict positivity of Hessian is expressed here by this theorem. We need to check the sign of the decay, the determinant decay, to have a strict convexity. So we characterize a function that is strictly convex by the positivity of the determinants. The strictly concavity by the positivity of the alternate, the products. Okay, so that's the decay. We know then the value of the determinant decay, the leading minors of the Hessian IHF, which is very nice. It connects, yes, a way that connects just using computing determinants, which is feasible, even for large dimensions. We can use, it's like polynomial operations, multiplication and addition. You can use a computer to do that and to check the sign. You see, it's much practical than checking the definition. Okay, so this is about strict convexity. But if you look here, we didn't need really a strict positivity. You see, we need just large. To have large, so these criteria is more restrictive. Okay, it imposes more for because we can have 0. What if it happens 0? Do we have convexity property or not? Yes, we have. This is the third test. This is marginal, so you can use this one. Okay, so this one is marginal. Okay, so let's put it more bigger. So here is the theorem, what it says. We need convexity of a set S, C2 function, regular, secondary. Here this time we compute the delta K. Delta K, we call them principal minor of order R. In the Hessian, they are determinants that we obtain by deleting n minus R rows and n minus the corresponding n minus R columns of the same numbers. Okay, so this is, yes, it's marginal. It gives that if we check this, so we have an equivalence. Okay, here you see you have just an application. If you have this, then you have strict convexity, so it is restrictive. Here to be sure to have convexity for C2 function, it is equivalent to check the sign of this determinant. Okay, we have more determinants to check, but we have the total information, total answer. Either we have convexity or not for a C2 function. Okay, so this is yes. So having now, yes, the conclusion. What about now our what about the conclusion about the extreme value theorem? Yes, we have the answer now. Here is the theorem. Let's write it now. So the answer to this is through the following theorem. It says that for S convex, let's see, S convex, x star an interior point to S, okay, f C2 function, f from S to R C2 functions, okay? Then X star C2, let's say for example convex CF convex. Let's add the case respectively concave. Okay, so we know each characterization for convex and concave. Okay, sorry. And it's for concavity, you need to check the sign of this determinant. Okay, so we have C2. So if we have an anterior point, then X star, look, X star is a global minimum for convexity, minimum, min, respectively max. For concavity, we need concavity for max if and only if you have just f prime of X star, that is gradient of f, or just let's write just gradient. Okay, gradient of f at X star equals 0. Okay, so this is the main theorem we have. Once we check the convexity or concavity of our function, then of C2 function, then having if you have a critical point, it will be then, if it is convex, you have it is global minimum. If it is concave, yes, X star will, the critical point will be a maximum point, global maximum point. Okay, great. So let's do one, two, or maybe two examples. First example is with the function of xy equal x4 plus y4. So I want to do this particular example. So what about convexity? So we have a gradient of f. Yes, it's 4x3, 4y3. We know that 0, 0, so gradient of f at 0, 0 is 0. It's the vector 0, 0. So we have a critical point, the only critical point. Now what about concavity? Okay, concavity, so we need to explore the Hessian. What is the Hessian? So fxx is 12, so let's just write it. So 12 x2 and 0, 0 and 12 y2. But look at what happens now if we try to compute hf at 0, 0. At 0, 0 will give us the 0 matrix. But then that means the strict convexity, we cannot check it. We cannot use this theorem for strict concavity or convexity. But let's explore this, the second theorem. The second, so we can check for delta r, the order of r. So k equal 1. So delta 1 at 0, 0, at delta 1, we check now convexity, okay? Convexity. Delta 1 xy is of order 1, okay? Of order 1, so delta 1 with order 1. So I have a choice to eliminate first column or second. Okay, so if first row or second row. So if I eliminate the first row, let's put 1, eliminate. Okay, so if I eliminate the first row, so I will get just 12y2. 12y2, okay, which is positive. Okay, now if I eliminate first order, k equal 1, first order, okay, here eliminate, eliminate first row, okay, delta 2 second row, I eliminate second row, so I will get 12x2, okay, which is positive. Eliminate second row, Okay, so it's, yes, if you eliminate second row, you eliminate at the same time second column, you are left with this quantity. Now k equal to, this is second order. Second order is obtained by eliminating n minus 2, so n minus k, which is 2 minus 2 equals 0. 0 eliminate, no elimination, so eliminate 0 rows. We don't eliminate anything, so that means we consider the whole determinant, 12x2 0 0 12 y2, which is 144 x2 y2, which is positive. So yes, we have always, we have so delta k xy positive for any k, for any order. Okay, then f is convex, and 0 0 is a global mean. Okay, and this one we can of course see it manually. We can check manually, check for this situation. It's easy to see that fxy, which is x4 plus y4, is greater than f00. Okay, always, which is 0 for any xy. So we are checking the definition. Okay, so you see how we compute this, check the, okay, the convexity of the function, find the critical point, and conclude. Okay, so this is just what I wanted to say, and yes, I think it's so this is global, how we can check about global extreme point using what, convexity. Okay, we use it here something, yes, and convexity, concavity. So we can use concavity, convexity, convexity, and global extreme points.